Welcome to the chapter on evaluation and benchmarking. My name is Marcel Wewy, and in this first section we will look at the big picture, why evaluation matters, what makes it hard, and why it becomes even more critical in the context of automated machine learning. Let us start with the most fundamental question. Why do we need evaluation at all? The answer seems obvious at first. We want to know how good our model is. But what does good actually mean? In machine learning, we are not primarily interested in how well a model performs on the data it was trained on. Any model can memorize training data given enough capacity. What we care about is whether a model has learned something meaningful that transfers to new unseen data. We call this generalization. So the main goal is we want models that generalize well to unseen data. This immediately introduces a challenge. We never directly observe generalization performance. We can only estimate it from the finite data we have available. And as we will see throughout this chapter, that estimation process is full of subtle pitfalls. The most familiar pitfall is overfitting. A model fits the training data so closely that it fails to capture the underlying pattern and instead captures noise. When such a model encounters new data, it performs poorly. But there is a second, less obvious pitfall that becomes relevant specifically in AutoML. And that is that AutoML systems introduce additional stochasticity and selection effects that make naive evaluation misleading. We will unpack exactly what this means in a moment. For now, just keep in mind that the goal of this chapter is to equip you with the evaluation protocols and benchmarking practices needed to mitigate both of these failure modes. So, why is evaluation hard? Let us go through the key reasons. First, data is finite, but we want to reason about infinite future data. Any estimate we compute from a finite sample carries uncertainty. The smaller the dataset, the larger that uncertainty. Second, models are stochastic and data is noisy. Running the same training procedure twice on the same data can yield different models, and therefore different performance estimates. This means that a single measurement is not enough. Third, and perhaps most sneaky, small design choices change conclusions dramatically. The choice of train test split, the choice of performance metric, the way preprocessing is applied, all of these can flip which method appears to win a comparison. Fourth, strong optimization methods can exploit weaknesses in the evaluation procedure. This is what we refer to as meta-overfitting. When a system is powerful enough to search over thousands of configurations, it becomes powerful enough to find configurations that just look good on the validation data purely by chance, without actually being better than any other model in a meaningful sense. This last point leads us to a conclusion. If evaluation is weak, progress becomes an illusion. A method that relies on flawed evaluation protocols will reward methods that game those protocols rather than methods that solve the underlying problem. Let us now make the distinction between overfitting and meta-overfitting precise, because it is central to understanding why AutoML requires particular care. Overfitting in the classical sense is a property of a single model. The model has been trained on a dataset and it has fit the dataset so closely, memorizing noise that it no longer captures the true underlying pattern. You will recognize this from any basic machine learning class. High training performance, but the test performance is poor. Meta-overfitting is different. It is not a property of a single model, but a property of the search process. An AutoML system evaluates many candidate configurations and selects that one that performs best on the validation data. Even if every single candidate is a perfectly reasonable model, the act of selecting the maximum over many noisy estimates produces an optimistically biased result. The selected configuration may generalize poorly, not because the model itself is too complex, but because the selection process exploited noise in the validation scores. This is a subtle but important distinction. A model can be simple and well regularized and still be the victim of meta-overfitting, simply because it happened to be evaluated at the right moment on a favorable data split. The key takeaway is overfitting is a property of a single model and meta-overfitting is a property of the search process and it needs to be remedied. Let us make this concrete with a simple example. Suppose 5 evaluated configurations, and for the sake of argument, assume all configurations generalize equally well with a risk of 0.2. Because we are estimating performance from finite data, each validation estimate is noisy. Each measured score is the true performance plus minus some random error. Now the system selects the configuration with the lowest measured score and reports that score. What happens? Well, even though no configuration is genuinely better than any other, the reported score may easily have a performance as low as 0.15 or even lower, purely because we are taking the minimum over the various noisy measurements. This optimistic gap is not real progress, it is pure noise presented as a result. The conclusion? Well, naive evaluation reports the best noise, not the best model. We have already touched on this, but let us be explicit about why evaluation is particularly critical in the AutoML setting. AutoML systems automatically explore large spaces of different models. This is their strength. They can consider far more options than a human practitioner working manually. But this strength has a direct consequence for evaluation. The more configurations we try, the easier it becomes to overfit the evaluation process itself. Every additional configuration we evaluate is another opportunity for the selection effect we described earlier to manifest. A human practitioner might try 5 or 10 configurations before settling on one. An AutoML system might try 5,000. The selection bias accumulated over 5,000 evaluations is far larger than the bias accumulated over 10. Automation amplifies thus bad evaluation practices. A flawed evaluation protocol that is manageable when applied manually becomes seriously misleading when applied at the scale of AutoML operations. This is why AutoML applies evaluation methods systematically, and why validating models correctly becomes even more important, not less, when the search process is automated. So far we have focused on evaluating single models, but in research and practice we are often interested in a broader question. How does one method compare to alternatives? Not just on one dataset, but across many different problems. This is the distinction between evaluation and benchmarking. Evaluation asks, how good is a model on a given task according to some performance metric? Benchmarking, in contrast, asks, how good is a method compared to its alternatives across a diverse suite of problems? Benchmarking is not just a technical exercise. Benchmarks shape research directions. When a community agrees on a standard benchmark, it implicitly agrees on what counts as progress. This is enormously powerful, but also enormously dangerous if the benchmark is poorly designed. Poor benchmarks reward shortcuts instead of real progress. A benchmark that is too narrow, or that leaks information, or that is dominated by a single type of problem will consistently favor methods that happen to be well suited to those specific conditions, not methods that are genuinely better in general. Good benchmarks, on the other hand, enable reproducibility, comparability, scientific progress, and reusability. They give the community a shared language for measuring improvement and identifying failure modes. In practice, we compare AutoML systems using anytime performance plots, visualizations of the best performance found so far as a function of time or the number of function evaluations. These plots reveal the full trajectory of the search, not just its endpoint. But producing these plots correctly is non-trivial. A single run is not sufficient, we need multiple runs to account for stochasticity, and we need to aggregate them honestly, with appropriate uncertainty quantification. How to do this correctly is one of the topics we will cover in the plotting section of this chapter. Let us close this overview with the guiding questions that will drive the rest of the chapter. How can we estimate future performance using only limited data? This is the subject of the section on evaluation of machine learning models, where we will cover holdout validation, cross-validation, and their practical trade-offs. When is one model truly better than another? This requires statistical testing. We need to go beyond point estimates and reason about whether observed differences are significant or could be explained by chance. When is an approach better than another? This scales the question up from individual models to full AutoML systems compared across many datasets, which is the domain of benchmarking. How do we avoid fooling ourselves when searching over thousands of models? The answer lies in nested evaluation, which we will cover in detail as a direct remedy to the meta-overfitting problem introduced today. And finally, how can we visualize optimization behavior rather than only final results? This brings us back to anytime performance plots and the correct way to produce and interpret them. These questions structure the entire chapter. Keep them in mind as we work through each section. By the end, you will have concrete answers and practical tools for all of them.